Hello. In this video, we're going to really start officially our study of infinite sequences by defining what a sequence means, looking at a bunch of examples, and talking about some of the properties that sequences might have. So a sequence is just a list of numbers in a specified order. So there's an order to it. They're not random. We can't shuffle them around. There's a first, a second, a third, a fourth number in the list, and so on and so on. And all of the time in our study of sequences that we're getting into now, we're going to always deal with infinite sequences. So you can assume when I say sequence that I have a list of numbers and it just goes on and on and on and on forever. There's no last number in the list. There's no end to the sequence. It just keeps going. So here's an example down here of an infinite sequence. 1, 2, 4, 8, 16, and then I put dots here to say that the terms keep going. And I'm hoping that you'll notice a pattern to be able to tell me what the later terms in the sequence are. But for now, we can use subscripts like this a sub 4 over here. So when I say subscript, I mean that 4 underneath. So I would say the fourth term of the sequence A is the number 4. Or if you're trying to say this out loud, you might say something like a sub 4 is 8. Or the fourth term of the sequence A is the number 8, because there it is right there. There's the first, the second, the third, and that's the fourth one there. By the way, that you might notice that these are all powers of 2. That was the pattern I was hoping you would pick up on, because 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, and so on and so on. So in that example there, I just gave you the first, 4 terms of the sequence, and then I put ... the ellipses to say the pattern keeps going. Hopefully you see what pattern I mean, and you can infer where the terms are going from there. That's one way to define a sequence, and a lot of the time we'll do something like that, as long as we're conversing with each other somehow to say and make sure that we know what the pattern is exactly. And that's why right here, hopefully there's an obvious pattern. Whoever's reading will notice it. Ideally, we'll be in conversation and we can confirm with each other what the pattern is. Like, for example, that one there, I see the powers of 2 sequence again. And so I just want to highlight here to say this sequence that I'm defining up at the top, I'm defining the exact same sequence in the other 2 things down here. So when I write this, I'm defining for you the same sequence. A sub n, I don't mean a different sequence A, I mean the same sequence that goes 1, 2, 4, 8, 16, and so on. A better, I would say, way to define a sequence is by explicitly defining a formula for what the nth term is. Instead of saying, there's a pattern, I hope you notice, this second way is saying, here is literally what the pattern is. We don't rely on any inference by the reader. That's why I say it's arguably better, and we'll try to do this when we can. So as I said, the sequence is the pattern is the powers of 2. So you might have noticed that 1 is 2 to the 0, and then 2 is 2 to the 1, and then 4 is 2 squared, and then 8 is 2 cubed, and so on. And that's why I have this n minus 1, because the first term of the sequence is the 2 to the 0 power. So the first term is 2 to the 0. And then the second term is 2 to the 1, or 2. And then the third term is 2 squared. And there's always this mismatch where I have the first term, and that has to equal 2 to the 0. And then I have the second term, and that has to equal 2 to the 1. And then the third term has to equal 2 squared. So the pattern that's going on there is that, in general, the nth term of the sequence is equal to 2 to the power that's 1 less than the number. So for example, what's the 10th term of the sequence? I wouldn't have to write out all of the terms along the way to rest assured that it's going to be 2 to the 9. And that's, I think, a good way to think of what I mean by explicit formula. It's a way to directly answer questions like, what's the 12th term of the sequence? What's the 378th term of the sequence? The explicit formula is something that I could just plug in an ordinal number, like first, second, third, 378th, to plug in an n and come up with what the corresponding nth term in the sequence is. Another way to define a sequence is recursively, or in other words, in a pattern to show how a term depends on the one right before it or earlier ones before it. When I say recursively defined, I mean how terms depend on the prior terms. And I want to emphasize again that this is the same AN sequence that I'm talking about down here as I was up here. The powers of 2 sequence that we're looking at all on this slide, that's the same sequence I'm defining down here. So I'm saying a sub 1 is 1, the first term is 1, and then I'm saying that the n plus 1th term is 2 times the term before it. That's a way that I would think of that out loud. Think of the n as an arbitrary point along the sequence, the nth term. And this is saying if you double that nth term, if you multiply it by 2, you get the n plus 1th term. You get the one right after it. And so this would mean from the 1, I can double it to get the next term 2, and then I can double that to get the next term 4, and I could double that, and hey look, I'm getting exactly the powers of 2 sequence that I was describing in the earlier 2 ways of defining a sequence. And notice that I really did have to give you a sub 1 equals 1. I had to tell you what the first term was. If I only told you the pattern is each term is double the one before it, you would say, well, that's all well and good, but where does it start? How do I know what to start doubling? And that's why I had to give you the first initial term as well. Here's another recursively defined sequence, and I've picked this one because it's relatively famous. You may have heard of it before, worked with it in other mathematics courses. Even if you haven't, that's okay. You can do a quick Google search right now by pausing the video and find all sorts of information about it. It's called the Fibonacci numbers, named after an Italian mathematician in the, I think, the 14th or 15th century. And he's the one, by the way, who's credited with bringing the Arabic numerals that, like, you know, the 0 and 1 and 2 that we write, he's credited with bringing them from the Arab world to Italy and really popularizing them as a way to do arithmetic better than other things that people were doing, like Roman numerals. So we can thank Fibonacci for the way that we write numbers nowadays. So this particular sequence is defined by setting 2 initial values. The first term in the sequence is 1, that's what I see there, and the second term in the sequence is, hey, it's also 1. And then what's this recursive pattern that's happening here? It says the nth term in the sequence is the term before it, the n minus 1th. So for example, if n is 5, this would be saying f sub 4. So f5 would be f4 plus f3, or in other words, the first 2 terms are 1. That's what this stuff over here says. The first 2 terms are 1. And then the stuff that I highlight in blue says each term is the sum of the 2 before it. Fn is the one before it plus the one before that. So for example, f sub 3 right here, f sub 3 according to this pattern would say it's equal to f sub 2 plus f sub 1. Or in other words, the one before it and the one before that add up to 2, and that's why I get 2 as the third term in the sequence. Continue the pattern there. 1 plus 2 makes 3. That's where that term comes from. 2 plus 3 makes 5. That's another way to get there. 3 plus 5 makes 8. 5 and 8 makes 13, and so on and so on. Each time, 2 numbers right before something add up to the one that's coming next. And here's essentially how I defined that pattern in words. Here's how I defined that pattern in symbols up here. Those are both recursive ways of defining it, either in symbols or in words. And I said earlier that ideally when we can, I would like to explicitly define, give a formula for the nth term of the sequence, instead of saying, hope you see the pattern. And definitely if I didn't say anything up here at the top and I just gave you this list of numbers, I doubt that any of us would come up with necessarily the pattern of adding 2 before it to get the one right after it. That's a hard thing to see. But even harder, apparently, by the way, is coming up with the explicit formula. I'm just going to mention this now in passing. This is not something at all we're going to get into in our class. But I'll just say, you know what, there actually is a pattern. It's just seemingly, there's a formula that you could plug n in to get the nth term. It's just pretty complicated. So for example, the 1, 2, 3, 4, let's say the 5th number in the sequence, f sub 5, is 5. I'll leave it to you just to try for fun at home. Plug in n equals 5 into the pattern here, into the formula. And what you will get after all of that calculation is exactly 5 coming out. There's lots of root 5s, but apparently this dividing by root 5 at the end cancels everything else out. and you would get that output. Or if I plug in n equals 6, I would get 8 as an output. If I plug in n equals 7, I would get 13 as an output. I'm still amazed that this formula really works. But again, this is not something we're going to get into in our class. Focus on this example of a recursively defined sequence up here at the top. Okay, let's start to get into another example, other examples and another definition that I want to motivate. Let's explore some sequences, and I've picked these two to be pretty similar to each other. I'm going to choose the a sub n sequence to mean 1 over n squared. So this says the nth term is the reciprocal of n squared, and meanwhile bn is this thing, and we'll get to what that means in a second. Let's explore what a sub n is. The a sub n sequence, and I'll write parentheses around it just to show you I'm talking about a sequence. This would say 1 over 1 squared is the first term. 1 over 2 squared is the second term. 1 over 3 squared is the third term, and so on, and so on, and so on. And so let me just calculate some stuff. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. So these are all the reciprocals of the perfect squares. And it may help to visualize this by imagining a graph, essentially, of the sequence by saying, if I plug in n equals 1, 2, 3, 4, 5, and so on, what are the outputs? What are those terms? How high are they? And I can see here that these numbers start at 1, and then they go down to a quarter, and then a ninth, and then a 16th, and then they're going to decay down to 0. So in some sense, if I write out this sentence here, the limit of this sequence is 0, I hope that you can kind of see what I mean by that. Even though we haven't formally defined what I mean by the limit of a sequence, because in a way this corresponds to our notions from Calculus 1 of limits, that this limit of that function is 0. Kind of the same thing is happening here, except instead of allowing x to be any real number along the way to infinity, I'm only plugging in whole numbers, 1, 2, 3, and 4. And so in a way, the points on this sequence there, they're picking out values from along the curve 1 over x squared. I'm only essentially plotting particular points along the way. What about the bn sequence? How is that different? Well, bn is the same numbers, but they alternate in sign. So when I have here -1 to the n plus 1, I'll point out here that this makes the sequence go plus, minus, plus, minus, plus, minus. The reason for that is when n is 1, I'm going to get -1 squared over 1 squared. And when n is 2, I'm going to get -1 cubed over 2 squared. And when n is 3, I'm going to get -1 to the 4th over 3 squared, and so on and so on. And -1 squared, that's a positive. And when -1 is cubed, -1 times itself 3 times, I have 3 negatives, that's a net negative. -1 to the 4th is positive. Essentially, an even power of -1 is positive, and an odd power is negative, and that's going to make these terms oscillate in sign. So it's exactly the same numbers from the previous sequence A, the 1, a quarter, a 9, a 16th, and so on, but I'm going to alternate in sign, plus, minus, plus, minus. How is that different from the sequence we were just looking at? Well, these numbers are going to oscillate +1, and then -a quarter, and then +a ninth, and then -a 16th. And so they're going to oscillate around 0, but decay down to 0 in magnitude and absolute value, just like this limit was 0. If I introduce alternating signs to that, that doesn't change the fact that the values are getting smaller and smaller and closer to 0. Now, I'm using these two examples to introduce this idea of convergence, the limit of a sequence. And don't worry, we're going to come back and formally define what that is and look at many more examples. But I'm just trying to introduce the idea gently for now. So if this is a little fuzzy for the moment, don't worry, we're going to keep talking about these things. So a couple of terms that we might also use to describe the behavior or the pattern of a sequence is that a sequence might be increasing or decreasing. So for example, I will say a function is increasing when Well, you guessed it, when the numbers are getting bigger, when each term is bigger than the one before it. Another way to say that is when the next term, the an plus 1, the next term coming up, is bigger than or equal to the one right before it. In other words, if I take a term and I look at the next one, it got bigger or stayed the same value. That's what increasing means. And likewise, I can say a sequence is decreasing when each term is smaller than the one right before it. Or in other words, if I look at a term in the sequence and then I look at the next one, it must have gotten smaller or stayed the same value. That's what it means to be decreasing. So, for example, the an sequence on the previous slide, that was decreasing. We saw 1, a quarter, a ninth, a 16th. Those are that's a decreasing sequence. Let me just make one up off the top of my head here. I'm just going to call it Cn to be different. If I make it go 1, 1, and then a quarter, a quarter, a quarter, and then a ninth, a ninth, a ninth, a ninth, and then essentially what I'm doing is I'm taking the terms of the an sequence and I'm making them repeat twice, and then 3 times, and then 4 times, and then imagine I made the 1/16th occur 5 times. This is also decreasing according to our definition up above, because each term, if I look at the next one, it's either the same number, like in cases like this, or sometimes it gets smaller, like in that case. And that still fits the greater than or equal to, the or equal to part of that definition. And that's why I'm making a note here to say that essentially our definition of increasing and decreasing is allowing for terms to temporarily stay the same, to be flat, to be a constant. So you could also use some similar terms, and if you read about these ideas in other sources, other books, or online, you may see an increasing sequence referred to with strict greater than, not greater than or equal to. And then the kind of thing that we're talking about would be an increasing function means it doesn't go down, so it would be non-decreasing. Or in other words, you might see the example that we're looking at right now called non-increasing, because the terms never go up. They either stay the same or they drop down a bit. So it's not increasing anywhere. But this is just a quibble of terminology. And the word monotone is used in math to mean same direction, one tone. So if a sequence is either always rising or always falling, so if it's increasing or decreasing, then we're just going to call it monotone to cover both of those possibilities. But I'll just mention right here that the Bn sequence we were talking about on the previous slide, that one is neither decreasing nor increasing. The Bn we saw on the previous slide, go back to those values here. Notice how they were sometimes jumping up and sometimes jumping down in value. So from 1 it dropped to become negative a quarter, and then it rose to become positive 1/9, and then it dropped down to negative 1/16, and it would keep going up and down. So it went down this way, and then it went up that way, and then it went down, and then it went up. And I can see that from the graph. It went down, up, down, up, down, up, and so on. And so it's not rising always, or it's not falling always. So that Bn from the previous slide is neither, it's not monotone. And finally, another term that we might use sometime is bounded, to mean that the terms of a sequence are stuck between 2 upper and lower boundaries, 2 numbers that all of the other terms in the sequence must lie between. So I made a little typo on the slide here. So when you see that red thing there, I'm just crossing out something that I meant to change. So these are the same an and bn sequence that we've been working with for a couple of minutes here. The an sequence is bounded between 0 and 1. So look back at the terms of the an sequence, 1, a quarter, a ninth, a 16th, they're all decreasing down to 0. Notice that if I draw a horizontal line at 1 and a horizontal line at 0, all of the terms of the sequence stay inside those lines, inside those boundaries. In that sense, that's what I mean by the sequence an being bounded between 0 and 1. These are like the lower and the upper bars between which all of the numbers in the sequence stay. For the other sequence, Bn, it's also bounded, but it's not bounded below by 0. It's bounded below by, well, in that sequence, it jumped as low as -1/4, and then it kept going up and down from there. So I guess I could have been a little more precise and said the lower boundary is -1/4. But the bounds, we don't actually care whether they're perfectly equal to the minimum and the maximum value of the function. I would still be allowed to say those terms are bounded between -1 and +1. If I lay out those bars at y equals -1 and y equals +1, all of the numbers in the B sequence do stay between those bars. So this is still a true statement. And here's an example of a sequence that's unbounded, the n² sequence. Or in other words, if I wrote out some of the terms, n1² is 1, 2² is 4, 9, 16. This sequence is unbounded because the values are just going to grow, and no matter where I try to set my upper bar, eventually the n² number is going to pass up above it somehow. And this allows me to say it's not bounded above. There's no upper limit that this sequence does not cross. It will eventually get bigger than any number you could possibly imagine. But it is bounded below by 0. The smallest number is 1, and it just grows from there.